One of the most startling benefits to living on the island of Maui is the stars. Just about every night I can step out on our front porch and see thousands and thousands of them. The Milky Way, the planets and their orbits, shooting stars that leave streaks across the sky, it's all right there. If you ever visit, don't miss walking on the beach at night because this place is one of the best locations on the planet for viewing stars. And as it turns out, for viewing the star, our star. Look, I'm a designer and I love tinkering with telescopes as much as the next guy, but I can't begin to describe the enormity of the sun, its mass, its energy, its importance to everything and everyone that lives in the galaxy, let alone how you would try and take a picture of it. But as it turns out, I have a friend that can give us just a taste of it. Paul Jeffers is the Integration Execution Manager for the Daniel K. Inouye Solar Telescope that sits 10,000 feet up on the summit of Haleakala, the massive volcano that makes up most of the island. That's a mouthful, but what that basically means is that Paul coordinates the day-to-day activities at the site of the most advanced solar telescope on the planet, working to integrate parts of the system to bring the telescope to full commission operation. Paul's and my kids go to school together, and they've become close friends, and so we've all become close friends, and we've been hanging out a lot, drinking each other's whiskey, telling some good stories. Recently, Paul and I sat down in his kitchen while the kids played in the pool out back, which you'll hear during our discussion, and he attempted to help me comprehend one of the most Herculean tasks in all of astronomy, taking high-resolution video footage of the surface of the sun. I went up and toured the telescope. My brain turned to mush trying to process what you guys do up there in terms of how you take a picture of the sun. So just for context, when was it those photos came out?
January, February this year, the National Science Foundation, who funds the telescope, they released our first light images, which were the first images of the sun's surface at the resolution that we're able to capture.
Ever.
Though that level of detail has never been seen before of the sun, simply because no one's ever pointed a 4-meter class telescope. And when I say 4 meter, that's the primary mirror of the telescope is 4 meters in diameter. So for our friends in the imperial world, that's what, 12 and a bit foot.
Just Google it. You can Google what a meter is if you don't know what a meter is.
Hey, as you can tell by the accent, I'm a child of the metric. I start counting in my fingers when people use inches.
You guys use a lot of terms up there that are concrete terms that we all would understand, but when you're talking about a mirror, you're not talking about a mirror.
The mirror in your bathroom, in order to give you that image of yourself when you look groggy and kind of dopey in the morning, it has the silver coating on the back side of the glass, so that whenever you wipe it and it gets all covered in fog, you just wipe it down and and it doesn't matter if you scratch the surface because the image is still good.
Right.
For us, we need to be able to actually recoat the mirror. So whenever that silver gets tarnished, we need to resurface it.
Right.
And so our mirrors are all finely polished, and then we front surface coat them. So we put a layer of silver, or aluminium in this case, on the front surface that is fractions of a hair thick.
Wow.
And then when it gets dirty or it gets tarnished, we strip it off and we put a new surface on it. The surface that you see and the perfection in the surface is actually the glass under the side. The aluminium just coats such a thin layer, it just mirrors, it prints through the pattern of the glass underneath. So if the glass isn't flat, the mirror isn't flat. And so all you do is you put this really fine layer of aluminium on top, and that causes the reflection. And when it gets dirty, we strip it off and we put a new one down. Yeah. And that's why it'll last 40 years.
Right, but when you say it gets dirty, we strip it off, you sound like you just kind of pull it out, strip it off, start a new one, and bada boom, bada bing. But you're talking about a process that takes...
Probably once we've practiced it, 5 to 6 weeks.
To clean a mirror?
To remove it from the telescope. So context, the mirror weighs like 2.5 tons. Jeez. So it's 2.5 tons of glass. And it's got this big piece of structure around it, this steel structure that supports it with all these little fingers that hold it.
Right.
And that's another like 7 tons. And so the whole thing has to be detached from the telescope. We take it down into the basement area. And then down there, we extract the mirror from its support system, from the thing that holds it. And then we take it away to clean it and coat it.
Jeez.
And so it's a long process.
It's crazy.
And it's the one that makes us most nervous.
Yeah.
It's our most valuable asset is that
How
mirror.
much does that cost? The mirror, how much, to build one of those?
I'm guessing, because it wasn't my part of the telescope, but I'm guessing that the mirror is probably of the $4 or $5 million just for the glass to have it made and shaped. Because the process, when they make the mirror, they mix up all the material for the glass and then they pour it into a mold. And then they take somewhere of the order of 9 months to cool it down because they want it to be homogeneous all the way through, and it's got these very particular characteristics, and if you cool it down too fast, it cracks. Wow. And so it takes a long time.
Yeah. Let's talk about the sun itself in terms of the surface of the sun.
So the caveat needs to be put in.
Yes.
You see in the introduction,
yes,
I used the word engineer.
Yeah.
Not scientist.
Yeah.
So whatever
You're
I
not
tell
a scientist.
you, I'm
Yes.
not a scientist.
Yes. No, but in terms of the surface of the sun, something you can talk to is we like to point telescopes at things as human beings. We like to see what's out there. And it started with this simple curiosity of what's out there and what it does and stuff like that. But the amount, the massive cost it takes to build, because I saw that thing, that telescope, I've never seen anything like that. It's something straight out of like the Avengers or something. And I'm looking at it going, why build it? What's the point?
So that I can talk to.
Okay. Let's talk about
that I know. So let's back up a step and go. Fundamentally, we as human beings, almost to a fault, don't question the merit of astronomy.
No, we don't. It's part of our human culture.
Inherently, I once heard it coined in such a way that if you get into a taxi and you wanted to, this is an astronomer talking, if you want to, you're feeling chatty and you want to chat to the taxi driver, the normal line is, what do you do for a living? Oh, I'm an astronomer. And the conversation just kicks in. Right. It can go from aliens to like stars to planets around other stars. Like we have as humanity, we have an understanding. Everyone can look up and see the stars. We can see the sun, and so we never question the merit of that research. Right. The same guy said, if I'm really having a lousy day and I don't want to talk, I say I'm an astrophysicist. No conversation.
No conversation. Oh,
that's astronomy nice. Is this. So we have this inherent desire to understand, to know what's going on.
Yes.
Nighttime astronomy and consideration of the galaxy is an area of astronomy that does not have as much impact on us. Yeah. We have one star in our solar system and it has a huge impact on us. Massive. We actually, the Earth exists within the outer realms of the sun. Like in the areas of influence or the atmosphere of our sun, we exist within it. The Earth is still within the atmosphere of the sun. And we are subject to different space weather, I suppose is the best way of putting it. Yeah. So you get things like coronal mass ejections. The Northern Lights. The Northern Lights is a classic, that shadowing and the colors and the beautiful, eerie, alien phenomena that you see.
Ethereal phenomena.
Yeah. Yeah. That is when stuff that's been ejected from the sun impacts the Earth and screws with our magnetic fields.
Completely.
We can predict, we've got about a 1 to 2 hours prediction window for that sort of stuff, detection.
Right. Solar storms coming off,
Yeah, if there's a coronal mass ejection heading for the Earth and there's a lot of stuff coming, we have warning systems that can get us up about an hour, 2 hours in advance.
Important because of satellites.
Satellites, power grids.
Right. Because what exactly is coming? It's just radiation.
It's radiation. They had an event back in late 1800s. I think it was called the Harrington event. And what happened then was they had a massive solar mass ejection. It was impacting the Earth. And there's stories told of actually seeing the Northern Lights from Mexico because it was such a big impact. Yeah. There are stories of telegraph operators unplugging their power supplies from the telegraph and being able to transmit. There's stories of telegraph operators being electrocuted. You get these magnetic fields and you get these really long lines. You create electric current. That's how we create electricity. It's magnetic fields and long wires. And so if you've got a really long wire and you put magnetic fields across it, you can create a charge. Right. And so they were creating that. That was back in the 1890s. Now we've got power lines going all across the US, all across Europe. All countries are subject to this. Imagine if you had the same kind of charge going into our power grid that was unexpected and unplanned for. you'd blow transformers all over the place.
Right.
The Department of Energy did a study a number of years ago and looked at the cost if we had the same size of event now, and they were like talking about years for recovery, because to replace these transformers, etc., to bring back the infrastructure after such an event would be phenomenal.
Wow.
So back to the original one, prediction of space weather. We detect it, and that's all we do, because our models of space weather are about, I'm guessing again, 40, 50, maybe 60 years behind our ability to predict Earth climates. So it's like mathematical modeling of weather. We can currently model with some level of predictability Earth's weather.
Yeah.
The sun, we are still in the dark. We don't understand the mechanisms. We are trying to understand them. And that is why we observe, because it's the basis of science. You come up with a theory, and you prove it by observation. And if it doesn't match, you modify your theory. Does it match now what you observe? No. And so at the minute, we can theorize to a much higher resolution on the sun than we can observe.
Right.
So the theorists can be off making up wonderful theories, but we can't prove them right or wrong. Right. And so we needed a tool, a device that would allow us to image at the level that will allow us to refine the modeling.
Okay.
Refine the theories.
Sure.
So do we understand really how the plasma on the surface of the sun interact? We're trying to get to that level.
Yeah.
And that's effectively the whole purpose of the telescope, is to allow us to observe at a level so we can refine and understand the mechanisms on the sun.
I think that myself as an audience members, I go, okay, that makes sense. I know when we saw the photos that were going up on the news, on CNN and on
New York Times front page.
New York Times front page. We saw those images. I remember seeing all these. It looked like cells. It looked like it. You know what I mean? It looked like these cells, dark areas, and
Granulations, what they call them.
Yeah, exact granulations. And I remember reading somewhere that was like, oh, each one of those cells is like the size of Texas or something like that, and they're magnetic. The dark areas were magnetic fields that were kind of being pulsing off of this thing. And I was like, oh, that's amazing. Now I know a little bit more why that's important. But I remember you saying when we first saw that, I remember you saying those are kind of PR images.
So we've done some initial like testing of some of our calibration systems. As a mechanical engineer, polarization is a black art. It is.
What is polarization?
So a lot of people polarize sunglasses.
Yes.
You hold your polarized sunglasses up and you turn them, like the light seems to change as it goes through them.
Right.
Like some things get dimmer, some things get brighter.
Right.
So light both has a direction and it has an orientation.
Right.
And the orientation, kind of like the angle that it's traveling at, is the polarization of light. I suppose that's not important in itself. What's important is that magnetic fields affect the polarization of the light.
Right. And when you're talking about light, you're talking about photons.
Yeah, the photons are the light waves.
But they have a directional. So if I'm visualizing and I see a photon, it has either a horizontal, diagonal, or vertical orientation.
Exactly.
Okay.
And also in the typical wave, you have a wave that travels.
Yeah.
But that wave also then can be, as you say, vertical. That wave could be going horizontal.
Right.
Or tilted.
Right.
Magnetic fields change the way that wave traverses.
Right.
And so the important thing is magnetism changes the polarization of light.
Wow.
So if you can measure the polarization of the light, how it's been transformed, then you can measure the magnetism and the magnetic fields by inference from that.
You're doing this so that you can adjust polarization? You can react to it?
No, so you're doing that so that you can then indirectly look at the magnetic fields. So we can't see magnetic fields.
Right.
You can't see a magnetic field.
Yes.
So when you have a magnet sitting on the table, you don't see the magnetic fields that are sitting around it. If, however, you were to shine a light source through it, as the light is modified by the magnet and the magnetic fields, if you can measure the way it's modifying the light, then by inference of observation, you can then measure those magnetic fields and see, and you can see the magnetic fields.
Right.
And so that's what we want to do, because the sun is all of the reactions and the things that are going on in the sun are, as the scientists have explained it, it's all about the magnetic fields. They are what are causing these like some of the polarization imagery I've seen is like you see these fields just twisting up and twisting, and then it's like they're a rubber band. They're wound and wound and wound, and then suddenly there's all this energy releases as they snap out, and then you get these mass ejections. The imagery we released as First Light was basically a diffraction limited image. Or near diffraction limited. And that is where the only thing we fully compensated for, or we compensated for the distortions in the atmosphere, and we compensated for all of the shape changes and the other problems with our telescope. And the thing that is left is the basic physics of creating an image. And that's the limitation on our resolution and the sharpness of our image. That's the imagery. That's what we produced. On the other side of that, what you would normally be doing is polarization as well. So you've got this image, but you also want to be seeing what is the magnetic field doing. We can't see
in a photograph,
but we want to be able to measure it to understand how the magnetic fields are changing and how it's affecting the sun.
So it's fun to look at those pictures, but scientists are just looking for that data. They want the data on
combination. It's like the polarization is where the real breakthroughs are going to happen. As so I'm told whenever we're chatting to the scientists. The imagery gives you context. Basically, you need a context. It's like taking an X-ray and never seeing what the X-ray is of. You know, sometimes they'll take a picture of where they're taking the X-ray of, and then you've got the X-ray. But if you don't have context for that image, it means nothing. But if you've got context, so this is what I see happening, and there's the driver behind it. So their legs all bent out of shape. Oh, and look, I can now see the X-ray, so I can see the legs broke. So it's the mechanisms behind what's going on is what they're trying to understand and then predict. And that's the big thing. You observe it, you model it, you predict it, you see if you can close that loop and say, does my theory, the premise that I'm using to predict, does it actually hold fast?
So the applications for a telescope like this are massive. Like in terms of communications, defense, everything.
As I said, we're government funded. So we're funded by the US government through the National Science Foundation. All our data is public access. So it goes, the scientists get first dibs at it and they know because they've requested it. But then it's public access. So we don't hold our data secret or we don't hold it back. We make it available. And so predominantly our scientists are after almost blue sky research in that they want to understand the mechanisms and understand it. You also then have other groups who are working much more fervently on the understanding of the mechanisms. And there's a number of other spaceborne solar missions going on, and so our data in combination with their data is actually really important to understand. So it's like looking at a problem but not just in one way, looking at it multiple ways. And again, checking that theory that you came up with actually fits in all the scenarios and all the ways that you can observe something. Because if it only works in one, but then you look at it another way and it doesn't work, well, there's something not jiving. And so there's a lot of cross-community cooperation, space to Earth-based.
Well, it seems like that would be kind of the best way to go about something this comprehensive, this massive, in terms of a challenge.
This telescope is like state-of-the-art. No one has built one like it. The last time there was a brand new solar telescope was 30 years ago. They've just released the first call for proposals, for scientists to actually think about, well, what would I like to look at on the sun with this telescope? And so we are massively oversubscribed.
I imagine.
There's a lot more people and proposals than we've got time to run, but it's gathering momentum as well. As people start to look at it, as different organizations, countries start to look at this and consider it a bit more, the interest builds.
There's one of the things that totally blew me away was this idea that you're going to open up the telescope. It's up in a dome, just like you would imagine on the top of Haleakala, and you open up the thing, and all of a sudden the full power of the sun is blasting into this series of mirrors. The amount of energy that's hitting that thing, the amount of heat that it's going to generate is hard to wrap your head around. And you guys have to somehow keep the whole thing from melting. Because how many mirrors are we talking about total? When the telescope is working, when you guys are actually taking an image,
the primary mirror, which we talked about earlier, is 4 meters diameter. Then we have a secondary mirror. The secondary mirror is mounted at the top of the telescope and directs the light back into the center axis of the telescope. And then we have a train of mirrors there that then direct it down to a laboratory below. Big difference between the solar telescope and nighttime telescopes is nighttime telescopes, you mount the instrument, the camera, to the telescope, generally speaking.
Yeah.
For us, solar physicists, solar astronomers, work in a much more laboratory type environment. It was a big adjustment for me coming from working on a nighttime telescope to a daytime telescope, because in the solar telescope we provide a large laboratory underneath the telescope where we direct the light to, and it takes 10 mirrors from your earlier question. 10 mirrors to bring the light down to the laboratory, and
you're bouncing it.
You're bouncing 10 different mirrors. All of them have a different purpose. Some of them are just part of the train of mirrors to get it down there, and some of them are adjusting and perfecting the image in different ways. And so each of them have a different role, and some of them move quickly, some of them move slowly, some of them don't move, and it totally depends on their purpose. Down in the laboratory, we have 4 instruments currently. We will have a 5th one. And so in the laboratory, which rotates, that has all these instruments, it rotates because you have to derotate the image, because the telescope, by the very nature of it, it follows the sun, but it doesn't compensate in the telescope structure itself for the sun not rotating. Does that make sense? So as you look at something and it does this arc through the sky, the telescope rotates around an azimuth axis. The azimuth axis is in line with gravity, and the altitude axis is perpendicular to gravity. And because they aren't aligned to the axis of rotation of the Earth, it then creates a rotation in the image of the sun as you track it all day long.
Right.
And so the laboratory downstairs, which is about 16 meters diameter, weighs 190 tons, has to rotate back.
The actual lab rotates.
The whole laboratory rotates, so that you don't then have the image rotating.
Inside the telescope, the laboratory that's receiving the light.
The whole laboratory rotates. And so the reason that we do this is so that we can create what looks like just a clinical laboratory, or not clinical, like an optical laboratory.
Yeah, but that's the one where we were seeing the guys in white lab coats and
all
the
the bunny suits and with the masks and everything. And that's because all in there are the instruments, and the optics are all exposed. And these are highly sensitive optics. And so everybody suits up just to try and keep as much dust and other contaminants out of the optics. So in the nighttime world, I keep jumping between the two, but in the nighttime world, you build an instrument, and you will have a science case for that instrument that will involve you looking at maybe thousands of different stars.
Yeah.
Say maybe you're looking for exoplanets, for planets that rotate around other stars. You'll build an instrument and you'll design it so that you can look at all these different targets. And you'll look at them exactly the same way.
Right.
And you will study them, but you've got thousands of targets to look at.
Right. And it's just checking box.
Yeah, exactly. And you'll look between them all. And so whereas what we have is one star where it's actually evolving and things are happening as we go. So we're only starting looking at one target. Effectively, there's different things to look at in the sun, but we're looking at one target, and so the way that we look at it has to be adaptable because it changes.
Yeah.
So the stars and things that are happening, exoplanets even, things are happening and evolve over days, years. You know, it's long duration observations. Right. For us, things evolve in minutes. So the sun's surface is boiling, the sunspots are forming and moving, and these things are actually, they're happening on a time frame that you actually create movies rather than take images. So so what we saw in what was plastered around like on the front page of the New York Times was one image out of the movie that was created. And if you look at the Inouye Solar Telescope website, you can see some of the movies that go with that.
Oh, you can watch footage.
You can watch footage. You can see the granulation changing and moving. Oh, and that's part of the whole deal about the observing the sun. It's not about taking one image. It's how is that image changing? What is happening on a time frame that we can relate to?
Right.
When we're doing imagery, we're making movies. We're not just taking a snapshot.
Wow.
And so, like a comparison is like Hubble did their deep space image took, I don't know, it was like hundreds of hours of observation, just staring at the one place, integrating, just letting the photons land on the detector and just staying focused on that one spot, just to be able to pick up enough photons to make one image.
Right.
Where we're shooting images every, 100 milliseconds, 80 milliseconds,
Right.
whatever number of milliseconds it is, and we're building videos.
Yeah, photons are not a problem in your situation.
Well, they actually are because, we're staring at the sun, but because we bounce it off 10 mirrors, and then we divide the light, because I was saying earlier about context, so you want to image it and you want to do polar. So because the sun evolves, it happens in real time for us.
Right.
You can't just go take a visible image and then come back and then go and do the polarimetry, because what you might have taken the image of might have changed, so you're taking the polarization of something else.
Right.
And so we divide the light. So as the light comes down into the laboratory, we will shoot off, and we will use filters and beam splitters and other things so that we cut chunks of the light based on frequency, and we'll send it to different instruments. We'll observe with an imager that's particularly working in the red wavelengths.
Yes.
And we'll send a whole chunk of the rest of the light to like a polarization system. And then we'll also carve off a little bit that we send to our wavefront system to be able to measure the image to perfect it.
You're talking about it as in like we're rerouting in water, like a stream.
Yeah, it's like you've got, that's a really good example. You've got this river coming down, and you've got different farmers on different sides wanting to use it, but everyone wants to use it at the same time. There's exactly the same amount of water coming down. So if you give this guy too much, the guy next to him starves. Yeah. So you got to balance it out. But if we're using 2 instruments plus our wavefront sensor, the time frame on our images has to be appropriate so that we get enough photons to be able to clock those images.
It is fascinating. So what do you do with the heat?
So the heat...
Because, it's got to be generating incredible amounts of heat.
So, again, I'm not exact numbers, but a 4-meter mirror collects about 13 kilowatts of energy. You can bring that down to what is a heater, like an electric heater. Yeah. And you get a couple of kilowatt heater. Yeah. So in itself, 13 kilowatts of energy isn't a lot. We focus it down to a primary focus, which is at the top of the telescope, to a diameter of about 50 millimeters or so, about 2-inch diameter. So we take the 4 meters, the 12-foot diameter, and then you focus it down to a section that's about 50 millimeters, 2 inches wide. That's more than we want. We only want a small section of that because our field of view, in astronomy you talk about field of view in terms of angle. Yes. So 1 degree, when you divide a degree by 60, you get arc minutes. And so our field of view is 5 arc minutes in size. That equates to our prime focus, where we focus down all that energy down to a 50 millimeter diameter. We actually only let a 12 millimeter diameter hole, like a 1/2-inch hole in the middle of that. Right. So you get a 2-inch focus, and all that energy is focused in that 2 inches. Yeah. And we only let 1/2 inch through. Yeah. And that is the bit that we're interested in. And then it travels all the way down. The rest of it, we dump. And that's part of the issue. We have to get rid of all that heat. Yeah. And so we currently reflect it onto the inside of the dome, and it dissipates out there. But that's not a good solution, because telescopes suffer from 2 things when you're trying to do what we're doing. You suffer from vibration. Yeah. Shakes the image. Yeah. It's like your hand when you're trying to hold the camera and it's shaking. Right. That's vibration, that's jitter. Yeah. And the second one is, if it's a hot day and you're standing on one side of a road and you're trying to take a picture of someone on the other side of the road, and you see a shimmer coming through the land, you see a shimmer coming off the road, that's called seeing. And that is whenever cold air touches a hot surface and it heats up, and it then is hotter than the air around it, and then it rises because it's less dense. Right. That effect, we can see it on a road on a hot day. If you have a surface that is 10, 15 degrees C or 20 Fahrenheit, just as a guess, above the ambient air temperature, then you get the same effect. Sure. And so we have got this 13 kilowatt heater with all this heat that we have to get rid of. And if we bounce it or we keep it somewhere, we let it land on something, that surface then starts to heat up. As that surface heats up, it starts to heat up the air around it, and we get this turbulence forming. Right. And that turbulence, it just destroys our image. Right. So currently we reflect it onto the inside of the dome. We will deploy, probably in 3-4 months' time, a new system where we actually reflect all that unwanted light onto a large flat plate. Right. So that's super black. Like it's painted with, or it'll be coated with like a non-reflective surface. Oh, wow. Wow. And then we run coolant through it. Yeah. And so we've I guess a couple of the engineers at our head office have spent a long time just analysing the flow through this black plate so that we can grab the majority of the heat. We're hoping we'll grab about 95% of the heat.
Yeah.
And then we pump that all the way through the building, through the telescope, all the way through the building. And then we have big heat exchangers in a separate building, and we flush that out.
Being a media and designer in my career, I'm always interested in how other people get into other fields. Because, you know what I mean? Because you can have a bit of tunnel vision when you're young, and especially if you get to college and all of a sudden you're with people that are like you. I'm majoring in graphic design when I was in college, and then spent my whole career in advertising and media. When did you know you were going to do this kind of thing?
I didn't. I had no clue.
No kidding.
I think I had one meeting with a career advisor, you know, the guy at school who, like when you're still in high school, and we back then had this kind of lame test thing that you did,
right?
And after you'd done that, you sat down with the teacher and they said, right, and he said, right, looking at your academics and looking at your
aptitude or whatever.
It was a career test. It was career interest or something. Basically it came up with mechanical engineering, electrical engineering, civil engineering.
Right.
And I was like, okay.
What's that?
And so I ended up choosing mechanical engineering. I went to college. I picked a college that did an internship during a year. So I did a year out in industry, which was really not common in the UK.
Right.
The company I worked for, I got a job with them afterwards. And then Joyce and I were engaged, and she was looking for work, or she was looking at colleges near where I was working, and I was looking for a job near where she was. And so I found a job in the Scotland near where she was wanting to go to college. And so we ended up there, and I worked in defence for 7 years. And to be honest, I was bored. I had a really good boss who left, and I had this really rubbish boss. And so combination of being slightly bored and a rubbish boss, I started looking for a job.
Yeah.
And this ad came up I saw in the engineering journal for a design engineer at the Royal Observatory in Edinburgh. And I thought, that could be interesting, I suppose. I applied for it, and a couple of weeks later I got a phone call to say, Mr. Jeffers, we really appreciate your applying for the job. But you didn't make the shortlist, you're on the reserve list for that. But we'd really like you to come in for an interview for this other job, which we think your experience and your resume make you really ideal for. And I was like, oh yeah, I didn't apply for that, so I don't. And they said, would you have time just to talk to the chief engineer of the observatory, because he'll tell you all about it. So I said, okay, and he called me then, and we chatted about it for a while, and it was the job of telescope work package manager, which was basically the engineer who was the technical lead for the mechanical part of the telescope. No optics, no instrument, no buildings, just the mechanical part of the telescope. So I talked to him a bit, and I said, yeah, okay, it's not very design, it's not as much design as. Sure. But I went for the interview, and turns out that they had lots of designers, lots of people who were used to doing optics and mechanisms and small stuff, but they had no one who'd done heavy engineering. Right. And I basically had spent the last 7 years in defence doing nothing but heavy engineering, like ships and submarines. And so they wanted someone who actually could work in that industry, work with the large fabricators. Right. And so that's how I kind of dropped into it. Right. And they said, oh, by the way, you'll have to go and live in Chile for a while as well. And I was like, I'll talk to my wife about that. Right. She was gung-ho, so. Right.
Oh, and so you've lived in Chile, you lived in Scotland, in Edinburgh, right?
Yeah.
Hawaii, of course, Arizona. Yeah. You're working, so kind of wherever there's telescopes now is kind of where you might be.
I'm really glad to be here now.
Yeah, it's not a bad place.
Normally, if I followed the same route as I'd done with the last project, we would be gone. We would be packing up and leaving because my part of the telescope is done. I moved into integration from having built the telescope itself, the mechanical part of the telescope. I stayed for integration, and they have offered me a job to stay on in technical operations, so I'm going to stay. It's really nice to actually stay, and so I know the telescope really well, but I know where all the things that need fixing, and we need to just. So the idea of sticking around into operations and actually getting the chance to iron out some of those things that just aren't quite right, and is really appealing at this stage.
Especially with the kids.
Yeah,
and
just
the
age and stage,
Yeah,
you know.
absolutely.
And this is a really beautiful place to stay.
It's not a bad place to be, for sure, man.
Hey.
You know what? Hawaii works well. You can do almost anything wonderful here. You can make podcasts. You can build a telescope. But your day is kind of funny, though, because my day wakes up and I can just walk into my office in the house and start editing podcasts. But you get up and drive from your house here at, what are we about? 2,000 feet elevation right here in Pukalani, and then you drive to the summit of a 10,000 foot mountain. You can't breathe up there. When I went up I remember just trying to climb the stairs inside the telescope and just going, oh my gosh. But you're used to that.
So I am. So I recently just got a Fitbit, and so it's interesting to see because I'm trying to figure out how. And it was like, this is interesting because I haven't had up in summit. So this week I'm going to see what my heart rate peaks out when I run the stairs.
Oh my gosh, it's incredible.
Because it'll be interesting because my resting heartbeat is at like 56 or something.
Yeah.
And I have no idea if that's good, bad, or ugly. But it'll be really interesting to see if I take the stairs 2 at a time and I go from ground to the telescope level, which is I don't know how many flights, but a lot of flights.
Yeah.
How hard my heart will be going.
And
It's good. It's good for your cardiovascular.
Yeah, no kidding. I was just amazed when we were up there, just how I just barely getting up those stairs was so winded. But
altitude's a really interesting thing from the point of view, like it's cumulative as well.
Yeah.
And so try doing your times tables at the end of the last day. It's just
exhausting.
7 times 6 is brutal after 4 days.
Yeah. Oh man, you see some beautiful sunrises on the way up though, huh?
Yeah, I texted you a couple.
Yeah, I saw a few of those pictures. It was jaw-dropping.
You know, it is totally understandable why it is considered sacred.
Yeah.
Because it is so breathtakingly beautiful.
Right.
Like from the clear days to the cloudy days to the days, even the days when you are completely socked in, and it is like I've been up there and after the ice storms, it is a otherworldly place.
Yeah.
It's really special.
So do you have a blessing?
Yes, I do.
You have a blessing for our people.
So I've used this a couple of times, and it is in many ways, it reflects both faith, where I come from, and what I do.
Perfect.
May the road rise up to meet you. May the wind be always at your back. May the sun shine warm upon your face. The rains fall soft upon your fields, and until we meet again, may God hold you in the palm of his hand. Amen.
The Voyagers podcast is produced by Sugarside Productions and recorded in Kula on the island of Maui. It's hosted by me, David Glenn Taylor. Special thanks to the National Science Foundation, the National Solar Observatory, and the team at the NOAA Solar Telescope, not only for the tour we were able to do, but also for the fantastic photos we were using on our social media. You can view a huge library of images and learn so much about the telescope at www.nso.edu. It's an amazing site. Go there, explore, and have a great time. You can also find them on Instagram at National Solar Observatory. If you enjoyed what you heard, please rate and review us on Apple Podcasts. It helps us grow the audience, makes new episodes possible. And if you're interested in supporting this podcast, go to www.voyagerspodcast.com and click the link to become a Patreon supporter. And to become a sponsor, let's just start a conversation by email. David@voyagerspodcast.com. Next week, we're staying on the island, but we're moving from the sky down to the sea. Here in Hawaii and elsewhere, the reef is in a fight for its life, and it needs humans to win that fight. Meet one of the leaders in that struggle, the Hawaii Wildlife Fund's founder, Hannah Bernard, and learn the latest on the health of our oceans. That's next week on the Voyagers podcast. Mahalo for listening, friends.
Yes, the neighbor's dogs.
Look at him.
I know. They're so.
That's gonna.
They are.
Let's wait till that one's done.
No, you see, the other one's going to join in now.
Yeah, I see it. That's a husky.
Yeah, so there's an older husky and something else, and they have got a bunch of separation anxiety.
Well, oh, they're gone. The owners are gone.
No, the owners are probably there or are not around or just have gone out for the day or something, and they start this. When they went on vacation a couple of years ago, these dogs howled all through the night, every single night. I was losing.
That is unbelievable, man. Not ideal for recording podcasts.
They're just like, and they'll get over it, and then they'll stop. But they just go through this. There's one less. I can't remember what his name is across the road, but his dog died, and then there's one less. But they still howl.
That's crazy. Okay. Let's go back a bit though. Actually.